In this question, we have two media. The interface separating two media is called boundary or interface. When you have separation of two different media, we need to obtain or we need to identify what exactly is happening across the boundary separating two media. In this example, region 1 where mu r1 is 4 is the side of the plane y plus z equal to 1. The equation of the plane which is given y plus z equal to 1. So, the boundary or interface is defined by a plane equation. It is not a simple boundary. If it is simple boundary like x equal to constant, y equal to constant or z equal to constant, we can decide unit vector normal to that, or you can decide directly tangential components. If it is x equal to constant, y, z are tangential, x is normal component. But when the plane or the interface which is defined by the equation, you must evaluate the unit vector normal to it. I will give that formula later. Before that, we have a plane y plus z equal to 1 containing the origin, means medium 1 is origin side of this plane, mu r1. In region 2, we have other side, definitely it is mu r2, which has 6. If the magnetic flux density in region 1, which is given B1 bar, you have to take care here, sometimes they may give B2 bar, they will ask us to find B1 bar. You have to take care here. B1 bar is given 2 Ax cap plus Ay cap, Tesla. Then we need to find the magnitude of magnetic flux density in region 2 is B2 bar and its magnitude. So, if we know B2 bar, we can compute its magnitude. Now, the unit vector normal to the plane, we can write An cap is equal to Ay cap plus Az cap divided by square root of 2, 1 square plus 1 square. So, every plane can have its unit vector normal to it. If you have the plane equation Ax plus By plus Cz is equal to k, then its unit vector normal to it is Ax cap plus B Ay cap plus C Az cap divided by square root of A square plus B square plus C square, which is there in potential gradient. It is like gradient function del f by mod del f. In mathematics you might have studied. So, An cap we can find. From this we can calculate the normal component vector of flux density in medium 1, that is given by Bn1 bar is equal to B1 bar dot An cap multiply with An cap. This is the formula you have seen in vector algebra. Component of A bar along B bar, it is giving us just component. We need component vector along the unit vector normal to it, which is B1 bar dot An cap is multiplied with An cap. So, from this we can estimate Bn1 bar. So, Bn1 bar is equal to B1 bar we have with us, it is 2 Ax cap plus Ay cap dot An cap Ay cap plus Az cap divided by root 2. This is our An cap. So, after this we have to multiply with unit vector along this direction. So, what we have Ay plus Az divided by root 2. You have to take care here while doing the dot product. Ax dot Ay, it is the given B1 bar which consists of B1 bar is given 2 Ax cap plus Ay cap. This is the given vector B1 bar dot An cap. So, we will be having Ay cap plus Az cap divided by root 2. When you are taking dot product, Ax dot Ay, we know that because they are orthogonal, its dot product is 0. The dot product between the two different unit vectors will be 0. The dot product with the unit vector itself is 1. So, we will be having Ay dot Ay 1, Ay dot Az is 0. So, from that, upon the simplification, we will be getting a Bn1 bar. That Bn1 bar is 0.5 Ay cap plus 0.5 Az cap. So, this is our Bn1 bar. Once we know this Bn1 bar, we can compute Bt1 bar also. That is, we have B1 bar in general, it is a vector sum of tangential and normal vector components, Bn1 bar. We know the Bn1 bar, and given is B1 bar, we can compute Bt1 bar is B1 bar minus Bn1 bar. So while simplifying it, we will be having Bt1 bar 2Ax cap plus 0.5 Ay cap minus 0.5 Az cap. So once we know this, we have to apply the boundary condition. The first step is evaluation or identification of tangential vector and normal vector of the given data. From that we have to relate our boundary conditions, from that we have to compute the required tangential and normal vector components. So we know the boundary conditions, Bn1 is equal to Bn2, or we can write Bn2 bar is equal to Bn1 bar. We know Bn1 bar already we calculated, so it's equal to 0.5 Ay cap plus 0.5 Az cap. Another boundary condition, we have tangential components of magnetic field intensity are same. Ht1 is equal to Ht2 if the interface has current free. So from this we can compute Ht1, we can write Bt1 by mu1 is equal to Bt2 by mu2. So once we know this, we can compute Bt2 bar. Bt2 bar is therefore is mu2 by mu1 is multiplied with Bt1 bar. We can use Bt1 bar here, and the given medium properties mu2 and mu1. If you know mu2 and mu1, we have mu naught mu2, mu naught mu1. By substituting them, we can compute B2 bar. So we will be having 3Ax cap plus 0.75 Ay cap minus 0.75 Az cap. So once we got Bn2 bar and Bt2 bar, by taking vector sum of tangential and normal components, we can estimate B2 bar. Therefore our B2 bar is Bt2 bar plus Bn2 bar. So once we obtain this, we can find the magnitude of magnetic flux density. So if you know this B2 bar, by substituting Bt2 bar and Bn2 bar, we'll be getting 3Ax cap plus 1.25 Ay cap minus 0.25 Az cap. Therefore our B2 is magnitude, is nothing but magnitude of flux density in region 2, which will be equal to around 3.259 Tesla. This is your answer.